Hi. So we talk about the shells, the main shells in the uh, electronic configuration. So shell number one, named K, it has one subshell named S. So it is a one shell, one subshell. It's a one orbital, and the code is S and can host maximum of 2 electrons. So if we come to see the drawing here of the hydrogen is have in the nucleus have one proton positive and has one electron around surrounding the nucleus, one electron. So electron configuration can take the code 1s1. So it's a 1, that's the n number, which is the main shell. S is the orbital subshell. 1 is the electron, number of electrons here. So when we put it in a like a square orbital, we can put only one arrow standing to the top, and so it is clockwise motion, and it's a 1s1. When we come to helium, so it has two protons. Helium atomic number is 2. So the 2 occupies the first orbital and the first shell, the shell 1. So it has, when we say helium 2, it means 2 electrons. 2 electrons always equals to 2 protons in the nucleus. So, and here there is no so the nucleus is positive charged, and outside we have 2 electrons. So the 2 electrons, they spin or they circulate, they move. One of them is clockwise as it is standing, the other one is anti-clockwise, so they can occupy both less repulsion in a one orbital. So when you reverse them or put them opposite, opposite means the standing arrow is on clockwise movement, the opposite arrow is the anti-clockwise movement. In this way they can sit together. If you put them both on standing, like this one, we make 2 of them here, so they will have a big repulsion, so they will move or circle clockwise, both of them, and they will create lots of energy to repulse, and that's make the orbital unstable. So here we can see we put them opposite sides, opposite direction, and then they can sit here. So the orbital here is 1s2, not 2s2. So because 2 is the shell number 2, we are talking about shell number 1. So it's a 1s2. The 1 here is the n, which is the main shell, and we call it K. S is the orbital, S, and the 2 is number of electrons in the orbital. Okay. Now we come to the shell number 2, the main shell of the atom, called or named L. So K, L, M, N, O. Second one is L, has 2 subshells. It means 2 suborbitals. The first one is S, the second one is P. So we give them both to the left side, we put number 2. So the shell number 2 will go to 2s and 2p. So S is one orbital, one suborbital. The P is the 2p, has 3 suborbitals inside them, and then the maximum electrons can take are 8 electron, 2 maximum filling in S, 6 maximum filling in P. Why? Because every subshell can take maximum of 2 electrons. So 2 times 3 will be 6. So 2 here, 6 here will be 8 together. So the shell number 2 take maximum of 8 electrons. And then when we put the electron configuration, it will be 2s2, 2p6. Okay. Now shell number 3 called M. So KLM, that will be number 3. M, shell number 3 has 3 orbitals, S, P, D. So the S, as we said, take maximum of 2 electrons, P, 6 electrons, D, 10 electrons. So 2 and 6 and 10 total will be 18 electrons. So we call them, the shell number 3, we call it 3s2, 3p6, 3d10. Now we come to shell number 4, named N. So has 4 subshells, 4s, 4p, 4d, 4f. The L here is the orbital, which is S, P, D, F. We can put them as squares or blocks. So this is S, 1 block, P, 3 blocks, D, 5 blocks, F, 7 blocks. S can take maximum of 2 electrons, opposite direction. P can take 6. D can take 10. F takes 14. Why? Because 7 suborbitals, 7 times 2 will be 14 electrons. Every electron described by 4 symbols known as quantum numbers. So here now we can talk about the quantum numbers. The first quantum number is the principal quantum number, which is the main shell. Principal one is N. N can take number 1, start with 1. So N equals 1, N equals 2, 3, 4, so on. Secondary quantum number is the angular momentum of orbital. The angular momentum of the orbital is L. So the L can divide it into suborbitals, which is S, P, D, F. And the L can take 0, L can take 1, or D 2, or F 3. So if we say the orbital L is electron in L1, it means in the P. If we propose that the electron in L equals 3, it means the electron is inside F orbital. Sorry. The third or magnetic quantum number, ML. So the ML are these numbers here. The S has ML of 0, only one room, one orbital takes 0, as we said here. And P, 3 subshells, 3 suborbitals. The middle one is 0. To the right side should be -1. To the left side, +1. So you cannot make them plus to the right, minus to the left. No, should be plus to the left. Okay, so now we come to MLD. D have 5 subshells. In the middle is 0, To the right, minus 1, minus 2. To the left, plus 1, plus 2. F is the magnetic quantum number ml, which has 7 subshells, suborbitals. The middle one, 0. To the right, minus 1, minus 2, minus 3. So these rooms are giving numbers. So if we want to know exactly where is the electron sitting, we have to go through ml. So ml define or determine the electron position. And now we come to the fourth quantum number, which is the spin quantum number. So that's related to electron direction. Electron direction, if it's spinning up or clockwise, we give it plus half. Let's go with plus half. If it is the lower or anti-clockwise spinning of the electron, so the number takes of the spin is minus a half. Now we come to the electron configuration of some selected atoms. If we come to the helium, so we talked about hydrogen. Hydrogen was 1s1. Helium has 2 electrons, atomic number 2. So 2 are sitting in the K. So the N equals 1. This is 1. S, the orbital. 2 are the electrons inside this orbital. So helium is saturated, is filled, last and only orbital has is 1s. So this is fully occupied by 2 electrons, and helium is 1s2. That is the top of the noble gases. So now lithium, 3 electrons. We start with 1s2, fill the 1s2 first, and then jump to the next one is 2s1. So as we said, 1s is only one suborbital, one orbital, one main shell, and that's it. We fill it with 2 electrons, and then what's left here is only 1 electron. This 1 electron will jump to occupy 2s1. So there is 1 electron in the main shell too. 1 electron. So in total there are 3. Fluorine, 9 electrons. Okay, 9 electrons. So we start with 1s2 being filled, jump to 2s2 filled, and then we can use the other orbital 2p5. So now if you count 2, 2, and 5 will be 9. 9 electrons for the distributed inside the shell number 1, shell number 2. So 2, 2, it means n equals 2. So it is these 7 electrons sitting, occupying shell number 2. 7 electrons. If you come to neon, same thing, filling 1s2 first, next orbital will be 2s2, third orbital 2p6. So now neon, the atom neon is filled with 10 electrons. There is no empty or singly occupied electrons. They are all 2 and 8. When you have 2 electrons filled, noble gas, 10 electrons filled, second noble gas, neon, fully saturated, fully occupied. We always put this underline as you see there, because we just want to separate these 2 orbitals. They are in the second main shell. Sodium 11. So now we start with filling 1s2, next 2s2, next 2p6, Now they are 10. One electron left. We put it in 3s1. So now we are using the third main shell. So the last electron. Why we talk about the last electron? Because the last electron determine the physical and chemical property of the atom. The last electron, especially the last electron. So if it is paramagnetic, diamagnetic, when there is a single electron, it's a paramagnetic. Chlorine 17. We start to fill the orbitals and the electron configuration starting with 1s2, 2s2, 2p6, 3s2, 3p5. Why we put 5? Because you count 2, 6, they are 10, and 2, 12, and 5, 17. So 17, what do we have here? Is chlorine. We have 7 electrons in the chlorine. So here we can just this related to this one. And now we messed everything. I think, are we doing well here or still? Okie doke. Yeah. Yes. Now we go to argon. The argon is 18 electrons, atomic number, 1s2, 2s2, 2p6, 3s2, 3p6. So now if you see argon, all electrons filled the orbitals, suborbitals. So we have 2 electrons in the main orbital, main shell K. We have 2 electrons and 6 will be 8 in the n equals, because 2 means shell number 2. Shell number 3 are fully occupied, 3s2, 3p6. They are 8 electrons. So here, as you see, we have argon 18. Argon, all the orbitals are filled, so it is the next noble gas. Okay, they are very stable. Noble gas, helium, neon, argon. Potassium, we have 19. So if we do 1s2, 2s2, 2p6, 3s2, 3p6, they are 18. We put here 18, so they are these orbitals here. And the next 1 electron left for potassium, we put it in 4s1. And here we have single electrons in the main shell number 4. Nickel 28, transition metal nickel has 28 electrons, 18 as 1s2, 2s2, 2p6, 3s2, 3p6, and then the rest. So we just made them short, not to repeat these electron configuration. So you can replace this 18, and the next. So what's left? If we have 4, we still 28. So we have 10 electrons left. We put 2 in 4s2 and 8 in 3d8. And then I will tell you how we arrange electrons in the electron configuration when there is overlap between 4s and 3d. So 4s comes first and then 3d. So now we have 4s2, 3d8. In the 4, we have 2 electrons. In the 3, we have 8 electrons. Okay, and then 8, don't forget 8 and 6 and 2 will be 18. So the 3 being used, 3s, 3p, 3d. All together here will be 16. 18 electrons in the main shell 3. Okay, now we come to krypton. Krypton is 36 atomic number, 36 electrons, 18 as we said here, 4s2 3d10, now the 28, and there is 4p6. So if we put all 3d10 and 3s2 and 3p6, 8 and 10, 18 in 3. In the main shell 4, you take 2 electrons in 4s2, 6 electrons in 4p6, 2 and 6 will be 8. So 8 electrons here in the subshell 4. Iodine, of course, the krypton fully occupied all the electrons, so it's the next noble gas. Iodine 53 atomic number. So now we collect 36 all together here, 36 of them. We call it as a krypton, and the rest will come as 5s2, 4d10, 5p5. So again here overlap, 5s comes before 4d, and then 5p will come. So in the electronic configuration or the orbital main shell 4, there are 18 electrons, and in the 5 n5, 5 here, 5 here will be 2 and 5, 7 electrons. Okay. Now we can put some questions and answers here. You can stop this video and you can look into these examples of questions. If we just take one, if ml we said the magnetic of the orbital, magnetic angular momentum of the orbital has the values of +1, 0, -1. Write down the value of L. So what is the orbital here? So when there is 3 suborbitals, they belong to P. So L is a P. So which number takes P? You remember? S, L equals 0 will be S. L equals 1 means P. So L is 1 and it's a p orbital. If L value 0, 1, 2 and 3, if the L value is 0, 1, 2, 3, deduce, obtain the value of N. So you have here an orbital has values of 0, 1, 2, 3. So what does it mean? There are 4 suborbitals here. 4 suborbitals. Who's the 4 suborbitals? They are n number 4, and they are 0 belong to S, 1 belong to P, 2 belong to D, and 3 belong to F. Okay, for n equals 1. So this is the main shell 1. Main shell 1 is what? Is S. What are the allowed values of L and ML? So it's an S, and the S equals, the L of the S equals 0, and the ML of the S has only 0. So 0 and 0. Complete the following set of quantum numbers. Okay, so you can do that. So if L equals 0, ML equals what? Again 0, and it's a S orbital. If N equals 3, So L equals what? And ML equals what? So N equals 3. L is 1. L is 1. S is 0. L is 1. P is 1. So it's a P orbital. And there is 3 before the P I have to put. And the ML for the P orbitals, they will take 0 in the middle, to the right -1, to the left +1. And so on. You can continue all these questions. Now, orbital energy of hydrogen and hydrogen-like species. Let's see what's the energy of the hydrogen atom. So every orbital is like a space could be occupied by 1 or 2 electrons, every suborbital. As the electron always on motion, it has energy depends only on principal quantum number n. So the n determine the size and energy of the orbital. And here the equation belongs to the energy of the orbital E equals -k divided by the n to the power 2. K is constant here. It's 1.3 times 10 to the power 3 kilojoule per mole. So the size of orbital, different values of n, but the same L and ML, 1s, 2s, 3s, 4s, so on, differ in their sizes. Of course, because the main shell, if we said here, has determined the size. So if 1s, the size is small. We go to the second one, 2s, size will be bigger. 3s, size bigger. Okay, different sizes. The larger the orbital relative size, the larger value of n. So whenever you have big value of n, 4, 3, 2, 1, bigger value, it means bigger size. So expected for elements in the S and P blocks of periodic table, but differ for the D and F blocks. Okay, so we stopped till here, and we'll see the next slides.